Good afternoon. This is one-dimensional antenna array optimization through gradient descent. The team that worked on this project was Spence Hannigan, Peter Tudor, and Carter Wysong. The outline of this presentation will be an introduction, a little bit about each gradient descent method that was used, and the results from the optimization in Python. Now to talk a little bit about antenna arrays and the problem that we're trying to solve. Antenna arrays are used all over the world and in many different technologies. They're on your car to determine how close you are to something else. They're on your phone to read signals like 5G and Wi-Fi. And they're in radar, such as the radar used in airports to find planes and other such applications. Standard designs use a uniform element spacing, as this is a good way to ensure consistent performance and a easily manufacturable design. But uniform spacing can cause higher side lobe levels and energy waste, especially when compared to other intelligently designed solutions. How can we minimize energy waste, or in this case even noise, as seen in the side lobes, while maintaining the same number of elements? The side lobe problem. Uniform spacing yields a strong main beam, which is intended, but a high side lobe level as well. A high side lobe level results in signal interference and wasted transmit power if transmitting, or wasted receive power when receiving, as antenna arrays can be used to transmit or receive signals depending on their polarity. And the spacing of these elements will be in wavelengths due to the fact that antenna arrays depend on their operational frequency. So the wavelength will determine how close or how far the elements need to be from each other. On the right, you can see two figures. The top figure is the uniform case, which will be compared throughout the presentation and shows a very low side lobe level, especially with respect to the random case below it, and it tapers off from about -15 to -25. While a randomly generated array, seen in the red graph, has an average side lobe level around -10 dB, and it stays quite high and doesn't have the nice tapering that you expect. Our objective is to break the uniform standard and optimize element position to suppress the side lobes. The gradient descent derivation goes as follows. There's two main functions. The array factor equation, which is then used to get the cost function that will be used throughout the gradients. The array factor equation is a running sum from 1 to capital N, where n is the number of elements in your array. W sub n is the weight of each individual element, and e to the jk x sub n cosine theta is the array factor contribution from each element's position and steering vector. In our optimization case, we considered cosine theta to be 1, as we did not intend to steer the array away from 0 degrees, and that's where all the information in main beam should be living. While x sub n was optimized for, and w sub n was optimized for, as these were the two search space parameters. The cost function includes two parts, a theta sub 1 part and a theta sub 2 part. This is to avoid minimizing the main lobe region, which we do not want to minimize at all. We want that to stay at 0 dB and to ensure that the area outside of that gets lowered. The distance between theta sub 1 and theta sub 2 is dependent on the number of elements and the spacing overall of the array, called the aperture. The left side lobe region goes from 0 to theta sub 1, and the right side lobe region goes from theta sub 2 to pi. Thus, applying the derivative to the complex magnitude squared, we determine the gradients of the cost function as seen below. And then the individual gradient descent terms that were used in the code can be seen below, and these are mainly coming from the chain rule. Now, to talk about all the individual gradient descents that were used. First is the original gradient descent algorithm full batch. An initial point is chosen, alpha sub naught, and for k equals 0 to the number of iterations chosen, the gradient descent is computed, and the function moves in the opposite direction of the gradient descent. And the update is, as mentioned earlier, where alpha of k plus 1 equals the previous location minus gamma, which is the step size, times the gradient at that previous location. The gradient of f in our case is gradient of c, the cost function as derived in the earlier slides. This algorithm stops when the gradient is small or the updates are tiny, which means that it has arrived at a local minimum. Now to mention gradient descent with momentum, the first iteration of gradient descent that was considered. We introduce an iterative velocity term that accumulates the past gradients, v of k plus 1, which equals beta v at the previous point minus the step size times the gradient at the previous point. where beta resides in 0 to 1 exclusive, is the momentum coefficient. Thus, we update the position by the following equation. Now on to stochastic gradient descent. Instead of cycling through points in order, each step chooses a random data point from that array factor that was mentioned earlier. A random point in the array factor is calculated, and then the gradient and then the cost at that point is found. And then from there, the array is updated, the positions and the weights that it needs. This function has the gradient of f sub I being the randomly chosen element, and has the same function as the normal full batch gradient descent. Finally, the LBFGS algorithm was implemented, and it accelerates convergence by approximating the Hessian matrix from the previous iterations of the gradient descent algorithm. Alpha of k plus 1 equals alpha of k, the previous point, minus alpha of k times the Hessian matrix times the gradient at alpha of k. The Hessian approximation is approximately the Laplacian of the cost function inverted. And LBFGS is the solution to a memory problem brought about by the BFGS, where the BFGS is O of n squared, which is the element count, and that is the memory requirement for this algorithm. In our case, our element count is just 16, so this doesn't become an issue. But for larger and larger arrays, this can lead to exponentially growing computation time, which is why LBFGS was used, which has an order of O of m times n, which uses only the last constant m gradient steps, which will be determined in the code. Finally, let's go over the results of our optimization algorithms that were implemented in Python. First, for comparison's sake, we have the uniform case, which has a final cost of 0.00424, an average sideload level near negative 29 dB, and a peak sideload level of near negative 13 dB. Now on to some details about the sideload levels and the plots therein. The maximum of the array factor sideload of the array factor plot will be 0 dB. Therefore, anything lower into the negative is better. You want to lower them as much as possible. The peak sideload level corresponds with about the strength of the noise seen in your signal, while the average sideload level will determine just how much noise you see. You want both of them to get lower, but if you had to choose between one or the other, the average sideload level is the intended minimizing quality, as average sideload level will keep noise out on average better than peak sideload level. The initial gradient descent has a final cost of 0.00787 and an average sideload level of negative 24 dB and a peak sideload level of negative 17 dB about. And once momentum was added, the final cost was approximately halved to 0.00312. The average sideload level dropped quite a bit to negative 37 dB, and the peak sideload level also dropped a lot to negative 23 dB. To improve even further, we considered the stochastic gradient descent, which used 0.00, which had a cost of 0.000155, an average sideload level of negative 42.67 dB, and a peak sideload level of negative 25.88 dB. Finally, the best of the algorithms and the one that created the lowest final cost was the LBFGS algorithm that had a final cost of 0.00108, an average sideload level of negative 43 dB, but a peak sideload level of negative 24 dB. This is a notable quality as the choice between stochastic gradient descent and LBFGS really depends on your intended minimizer, as LBFGS has a lower average but a higher peak, while the stochastic has a higher average sideload level but a lower peak sideload level. Therefore, depending on your implementation, you would want to choose one or the other. Finally, let's see the results and the plots. The blue plot on the left will always be the uniform case, and the red will be the array factor of our optimized solution. The naive gradient descent does cause the main beam to grow, as can be seen in the left plot, and has a unique action of stacking elements on top of each other after many iterations. This can be seen in the left plot, where the red lines are the element locations in terms of lambda, and the green line is the element weighting. The first and the fourth element, for example, could even be removed from the array as their weighting is so low compared to the middle element at 0, which has a weighting of 1, for example. The gradient descent, if allowed to run for a long time, will stack elements on top of each other, and these could be run at half power to even thin the amount of elements in your total array, which can allow for further optimization in cost of building the array, for example. Now for the gradient descent with momentum results. The general shape of the array factor plot is maintained, but the main lobe region was minimized back to nearly what it was when it was uniform, which is intended. And it can be seen that, unlike before, none of the weights are really pushed towards zero, and there's kind of an even distribution of the importance near the middle of the array, while it tapers off towards the sides. This shows that when using gradient descent with momentum, none of the elements can really be removed, and all of them maintain to the overall performance of the array. The stochastic gradient descent solution maintains the best shape in the side lobes so far, where they're almost flat coming off of the main lobe region, which is seen in the left plot, and the importance of the elements tapers off greatly as one moves towards the outside of the array. There's a general shift to the left due to the stochastic nature of the algorithm. It could shift to the right, or it could find other elements to be important, but overall it has a good result and shows that the side lobes can be minimized and kept relatively flat. Finally, the LBFGS algorithm shows the flattest of all of the side lobe regions, which are seen in red, and has an amplitude taper profile very similar to the stochastic gradient descent, but is shifted towards the towards the right, and has the elements on the outside once again as less important than the elements on the inside. Also, similar to the initial gradient descent, some of the elements have once again been moved very close to one another, which can be seen near 0.5 wavelengths in the left plot. Thank you very much for listening. Have a great day.